Yeah.
I think it's something just going to do every week Friday.
Yeah.
For the most part. Okay.
Yeah. Yeah.
Perfect. Thank you.
Yeah. So that way you don't have to think about it. It'll always be Friday at midnight.
Yeah, it just doesn't show me. I just want to write it on my schedule, but I figured I'd ask.
Oh, I see. It should tell you what the due dates and times are in the Prairie Learn system.
Yeah, it
Yeah.
does, but like with the homeworks that haven't opened yet, it doesn't
Okay.
show that.
I see. Yeah. That's right.
So,
Yeah.
okay.
I'll try to release homeworks with like a minimum of like at least 1 week where they're open. So
Okay.
when they're open, then the due date will always be Friday at midnight.
Okay.
Yeah.
Perfect. Thank you.
Yeah. All right, good morning, everyone. Welcome to the end of a snowy week. So, let's see what's on the agenda for today. There is the homework number 2 is due tonight at midnight. Remember, labs and tutorials will start next week, so please start showing up to whichever sections you're registered in. And then Lab 0, remember, has no pre-lab, so you don't need to prepare anything for the lab next week. Just show up to your lab section. Okay, so I'll spend a little bit of time talking about the format of the labs. Either be at the end of today's class or during Monday's class. Okay, so what we've been talking about recently is the electric field. And the picture we had was that if I place a charge somewhere in space, it will create an electric field that permeates all through that surrounding space. So that if I was to have a second charge somewhere nearby, that electric field from the first charge would exert a force on that second charge. In the same way, the second charge that I place in the space makes its own electric field, and it'll exert a force on the original charge. And it will be consistent with Newton's third law that the forces will be equal and in magnitude, but opposite in direction. Okay, and so we have this relationship that if we place a charge Q in an electric field E, the force that that charge will experience is Q times E. If Q is a positive charge, then the force it experiences will be in the same direction as the electric field. If it's a negative charge, the force will be in the opposite direction. Okay, and then we started talking about, okay, if I had a point charge, what electric field does it create? And we used Coulomb's law to figure that out. And we worked out that charge capital Q creates an electric field at point P given by Coulomb's constant times Q divided by R squared, where R is the distance from the point charge to P. And then the direction is given by R hat, and R hat is a unit vector, a vector of length 1 that points from Q towards that point P. All right, so what I want to do is I want to do an example to see how some of this works. And so in our example, we're going to have a coordinate system. We're going to have two identical charges, capital Q on the x-axis. One of those charges is placed at the position x equals plus a, and the second one is at the position x equals minus a. So both charges are at distance a away from the origin. And then we're going to look for what is the electric field at point P. And so we want the net electric field due to both those charges. We're going to assume that the two charges are positive and they're identical. Okay, so before we actually solve the problem, what I'm going to do is I'm going to make like a little kind of list, prescription for how we could attack this problem. So the first thing we're going to do is we're going to realize that, okay, I want the net electric field at this point P. And so I'm going to have contributions from all of the charges that are nearby. In this case, we have the two of them. And so our strategy will be to individually find the contribution of each charge Q to the electric field at P. And then once we've done that, we can add the contributions as vectors. And so that comment as vectors is important. So we're not just adding arbitrarily just two numbers. We have to add, say, the two x components together and then add the two y components. And so we have to consider the directions that these electric fields point in. Okay. The other thing that we'll do is we're gonna look for symmetries that are gonna simplify the problem. And again, this is where the physics is. It's all in the setup. And what we're gonna try to do throughout this entire course, Physics 121, is always look for simplifying symmetries. And so this is a very important point. And so look for simplifying symmetries in the geometry that will make the problem easier to solve. And when we get to this step, we'll really emphasize those symmetries that exist for the problem that we're about to do. Okay, so those are the two key steps. So the first thing we'll do is we'll just think about the electric field due to one of the charges. Let's take the charge Q that's along the positive X direction. And so I'm just going to draw a line that connects Q and P. Now we know that the electric field that we're going to have to calculate is going to depend on 1 over the square of the distance from Q to P. So the first thing we might do is write down that distance. And so we have a right angle triangle here. So what's the length of this hypotenuse, the distance from Q to P? Yeah, that's right. It's just a right angle triangle, so we can use Pythagoras theorem. And so it's a squared plus z squared. And so now we have that distance, which is going to be important. And then we take the square root, okay? So that we're not looking at the square of the distance. All right. Now, we said Q is a positive charge. We know from last time that electric fields point away from positive charges. And so we know that the electric field due to this first charge, so let's call this, say, charge 1. So we'll have a E1 that points something like this. And what I'm going to do is I'm just going to label this angle theta in our right angle triangle. And this angle here is exactly the same. All right. So if I was to draw the electric field due to the second charge along at position x equals minus a, it'll look very similar. It'll just be pointing off, instead of pointing kind of to the vertical and the left, it'll be vertical and right. So here's the symmetries. What are going to happen to the x components of these two electric fields? They're going to cancel exactly, right? We have identical charges, the same distance away from P, so their electric fields are going to have the same magnitude. And we can break them into x and y components. The two x components will be the same, but in opposite directions. What about the y components? What's going to happen there? They're going to add together. They're going to be identical, and they're just going to add together. And so what we can do is we can analyze only this first charge. We'll find the x and y components, and we'll say the x components are going to cancel. I don't need to think about the second charge anymore. And the y component will just double. Okay, and so let's make a note of those observations. Okay, for this problem, we would have that the magnitude of E1 would be equal to the magnitude of E2, but the x components are in opposite directions and will cancel exactly. the y components will be equal and in the same direction. And therefore, simply add. Okay, so this is the simplifying geometry or symmetry. So this is simplifying symmetry arguments. Okay, and so we're always going to be looking for these types of things when we solve problems like this. Okay, so let's go back to this problem here then. We're going to have an x component for this first electric field. This would be E1 x component. And then we're going to have, let's see, a y component over here. This would be E1, and it would be the y component. This y component, it's going to be the magnitude times the cosine of theta, because the green line is the side that's adjacent to our angle theta. So we're going to have cos theta. So E1 cos theta is what we have to remember. So from these symmetry observations, we can right away say that E net in the x direction will be equal to E net, let's say 2 in the x direction. E2 will have a positive x component, and then we'll minus the E1 x component, which has its horizontal component pointing to the left. And we'll say that these are going to be exactly 0. Okay, on the other hand, the net electric field in the y direction is going to be E1y plus E2y. And that's just going to be 2 times E1y. Because they're going to be the same, so we just double. And we've already said that that's going to be E1 times cos theta. So we have 2 E1 cos theta. All right. So what we have to do now is we have to figure out E1, the magnitude of the electric field, and we have to figure out cos theta. So we know that for a point charge, that E1 is going to be what? It's going to be Coulomb's constant times the charge divided by the square of the distance from Q to P. But we already wrote down that that distance was the square root of a squared plus z squared. And then, so we need the square of that distance, and so we end up with a squared plus z squared down here. So this is for our point charge. And so we have to think about this cos theta angle again. And so for cos theta, what we had is, we had this right angle triangle. We had Q was sitting over here, right? And then this was a distance A. And then P was sitting over here, where this was Z. Here's our right angle, here's theta, and here's the square root of a squared plus z squared. All right, so cos theta. Cos theta is equal to what? It's ka toa. Ka is cos is adjacent over the hypotenuse. What's the adjacent side here? Z, right? It's the side next to the angle that's not the hypotenuse, and so it's Z. And then divide by the hypotenuse, it's square root of a squared plus z squared. All right. So then what we can do is we can take this expression for E1, and we can take this expression for cos theta. Where does it go? Here. And we can insert this in and we can find the net electric field along the y direction. Okay, so E net in the y direction is 2 times E1, Coulomb's constant times Q divided by A squared plus Z squared times cos theta Z divided by A squared plus Z squared. Okay, the denominators are the same, except we have one that's inside of a square root. We can combine those and we could say, all right, what we have is 2 times Coulomb's constant times Q times Z. That's the numerator. And then we have A squared plus Z squared times the square root of that. So that's everything's to the 3/2 power. So finally, we could write then that the net electric field, it has no x component, so we could just put 0 times I hat, or we could just leave that off, plus 2 times KEQ Z divided by A squared plus Z squared of 3/2, and that's in the y direction, and that is our net electric field for this problem. Okay, so this is not a difficult problem, but the important points are to look for those simplifying symmetries. Notice we didn't do any calculations for that second charge. We just said it's going to produce things that are similar to the first charge. And then we separate our electric fields into components and then separately add the x components and the y components from the two charges. All right. Oh, someone else is joining. Let's get rid of this. All right. So I want to do one other thing with this problem, and I want to go back here. And I want to imagine what would happen if I took point P and I moved it way up the y-axis so that this distance Z becomes huge compared to A. I'm going to draw that. So let's consider, here, we'll keep this over here. Let's consider what happens when we make Z much bigger than A. So the point P is very far away from the x-axis. So I can try to draw that picture. And so let's really exaggerate it here. So here's my x-axis and here's my y-axis. Sorry, that should be a y-axis. And we're zoomed out now. So we're really zoomed out. And so we're going to have Q sitting here to the right. And then we have another Q sitting here to the left. And then here's our point P. And now this is Z is way bigger than A, right? The distance between the two charges is 2 times A. So if I was to look at the electric field at point P, what would I expect in this case? Without doing any calculations. What does it look like I have at the origin here when I'm sitting at P? Yeah. A is almost 0, or another way of saying the same thing is that it's almost like these 2 point charges are sitting at the origin, and we can't really tell that they're separated. And so it looks like we have a total charge of 2Q just sitting at the origin. So from the position P, so from the position at point P, it looks like we have a total charge of 2q. Oh, my 2 looks not like a 2. 2q at the origin. So if I did have a charge 2q sitting at the origin, and I'm sitting at point P, then I would expect that the electric field would look like, so we expect the electric field at P to look like that of a point charge of total charge 2q. And so we expect E to be approximately equal to, well, for a point charge, we take 2 Coulomb's constant times the charge. In this case, it would be 2q, and divide by the square of the distance from that charge to the point P. In this case, that would be z squared. And so if you look at this, what should happen is this expression in the red box should look like this expression that I'm going to put in the green box when z is much bigger than a. And so let's see if we can show that that is the case. So let's call this equation 1. We'll call this equation 2. And let's see if we can figure out how they're related. So we expect that equation 1 should become equivalent to equation 2 in the limit that z is much bigger than a. Okay, so equation 1 was, let's see, it was ke 2q z divided by z squared plus a squared to the 3/2 power. All right. If z is huge compared to a, what could I do with z squared plus a squared? How could I make a simple approximation? Let's say z is 1,000,000 and a is 1. What's 1,000,000 plus 1? It's about 1,000,000, right? Who cares if I have an extra dollar if I already have 1,000,000 other ones? And in fact, it's even more extreme than that because it's not z plus a, it's z squared plus a squared. So if z is 1,000,000 and a is 1, then z squared is 10 to the 12 and a squared is 1. And 10 to the 12 plus 1 is just 10 to the 12. So if z is much bigger than a, then z squared plus a squared is approximately just z squared. And z squared plus a squared to the 3/2 is approximately just z squared to the 3/2. But z squared to the 3/2 is just z cubed. All right, so then in the denominator we have z cubed, and we could say, well, in this case, the net electric field in the y direction is approximately ke times 2q times z divided by z cubed. And then, of course, we can cancel 1 power of z, 1 factor of z, and we get ke times the total charge divided by z squared as expected. Okay, this is a useful thing to be able to do, to say, look, I could have some complicated arrangements of charges as long as I'm very far away from that arrangement of charge, the geometry doesn't matter that much. If I'm very far away, it just looks like a point charge with total charge of the sum of all of the little point charges that are making up this distribution. And I should get KE times the total charge divided by the square of the distance that I'm away. It gets more complicated when I'm close to that distribution, but in certain limits, we can simplify things. Okay, good. Any questions about this example? Yeah.
You get a feel for when you make this approximation? Or you just say it?
Yeah, I mean, it's roughly, if approximately if Z gets to be about 10 times bigger than A, that's kind of a rule of thumb, like an order of magnitude, a factor of 10 difference. Yeah, something like that. Okay, but yeah, on a test situation, if I wanted to make you to make an approximation, I would tell you to what kind of approximation to think about. Okay. So I want to do something that's a little more tricky. And I want to start thinking about continuous distribution of charges. We won't do a lot of this type of calculation, but I want to show you how it works because it's useful in order to see how we can solve these types of problems using a little bit of thought and a little bit of insight. So what we're going to try to do is we're going to try to calculate the electric field due to a uniformly charged rod that is very long. Okay, so what I want to think about then is we have this rod that's really long. You know, I can only draw a section of it, but it keeps on going to the left and to the right. And so maybe this is the x-axis, and then over here is our origin, and then we're going to be sitting at some point P. And we're going to want to know what is the electric field at point P due to this uniformly charged rod. And so I'll draw a bunch of charges sitting on this rod. Okay, and so at first glance, this is a difficult problem, and it is more challenging than the one we just solved. However, there are some parallels that we could use. What is the direction of the electric field at point P going to be? Yeah.
Vertical.
Why?
That's the x coordinates kind of cancel each other out, and it's going outward.
Yeah, that's right. So what I could do is I could say, all right, I'm going to pick a small section of this charged rod, and I'll say this section that I color red corresponds to some piece of charge. I'll call it delta Q1. And just like we did for the previous problem, we could say, well, if I wanted to know the electric field due to this charge, delta Q1, it would just be something like this. But I could always find a corresponding piece of charge. Maybe it sits over here. That is delta Q2. And if I make this distance x equal to this distance x, then when I draw the electric field due to delta Q2, it's going to look like this, and we'll have an exact cancellation of the x components. And it doesn't matter where I choose delta Q1, like I could make it 2x away. I could find a delta Q2 that's 2x away, and again, the horizontal components are going to cancel. So from this argument, we can deduce without doing any calculations that whatever the electric field at point P is, it has to be perpendicular to the rod. So it's vertical in this case. All right. So by symmetry, the net electric field at P must be perpendicular or pointing away from the charged rod. Okay. And so I guess we would say then that the net electric field is going to be pointing something like this. Okay. So what we're going to do is we're going to employ the same strategy that we just used for our 2-point charges to see if we can construct something that will help us calculate the electric field due to this line, this continuous line of charge. So the strategy is going to be, let's figure out just the vertical component of the electric field due to some piece of charge delta Q, and then we'll add up all the vertical components from all of the little charges delta Q that make up this entire rod. And that method of adding up all the little pieces that contribute to the total electric field is going to lead to an integration. Okay, and so that's the plan. Okay. So to find the net electric field at P due to the charged rod, we add up all of the vertical components from the elements of charge delta Q that make up the rod. So I'm going to draw the picture again, and we'll label the right angle triangles and all those things, but it's all going to be exactly like we just did for the previous problem of 2-point charges. So we would have our charged rod, and then we would have our point P would be sitting over here somewhere. And what we're going to do is we're going to pick this delta Q here. And we're going to say, all right, delta Q is a distance X away. This point P is a height Z away from the rod. This hypotenuse is X squared plus Z squared. Here's the angle theta. So everything so far is exactly the same, except, you know, instead of distance A, we called it X. Otherwise, everything's the same. And the electric field due to this delta Q would be something like this. So this is E delta Q. And we would find the vertical components, which would be E delta Q times cos theta. Here's the angle theta. And we already know that cos theta is going to be Z divided by the square root of Z squared plus X squared. Okay, and so this would be equal to, let's see, Coulomb's constant delta Q divided by X squared plus Z squared. So that's just the Coulomb's law part of it. And then we multiply by the cos theta, which was Z over X squared plus Z squared square root. And so that we get KE delta Q Z X squared plus Z squared to the 3/2. And so you can see how all that same work that we did for the previous problem just carries over to this case. But what we have to do now is we have to now say that's the electric field at P due to just this one little piece of the rod. But we need a whole bunch of those delta Qs to construct that whole rod. And what's going to be different about each one of them is just the value of X. Some of them are going to be close to the origin, some of them are going to be far away, some of them are going to be positive values of X, some of them are going to be negative values of X, but we just have to add them up for all the different X's and all the different delta Qs that make up this charge rod. So the net electric field due to the entire rod is given by the sum over all the delta Qs that are needed to make up the rod. Okay, so then we could say E net in the y direction, and we'll only have a net electric field in the y direction, it'll vanish in the x direction, is the sum of all the delta Qs. So we would have like Coulomb's constant, delta Q, I'll put a little index I on it. So we'll have delta Q1, delta Q2, 3, 4, however many are needed to make up this long rod. And then we have to multiply by Z. Z's going to be the same for all of them. It's just the distance between the rod and point P, but each of the delta Qs will have a unique value of X. So we'll index the X as well. So Xi, and then it's to the 3/2 power. Okay. So in order to go a bit further, you know, that sum would be a hard sum to do because we'd have to figure out the X's for every single one of those delta Qs. What we're going to do is we're going to try to rewrite this in another way. So we're going to assume, let's assume that in a section of this rod that is length L, the total charge is capital Q. Okay, this rod is very long. In fact, what we could do is we could say it's infinitely long. And so if it's infinitely long, its total charge is infinity. However, we could say, look, I'm going to look at a 1 meter section of this very long rod. So L is 1 meter, and I'm going to count all of the charge that's in that 1 meter section, and then I can define a charge density, a charge per unit length, that is the total charge divided by whatever length I chose, 1 meter maybe. So then we can define a linear charge density or a charge per unit length of, people use the symbol lambda, so this is Greek letter lambda. And we're going to define it to be the charge of that length of rod divided by whatever the length is. So, you know, you're familiar for sure with like a volume density, a volume mass density, and there they use the Greek letter rho as the mass divided by the total volume. So we're going to continue with this Greek letter for these densities, something per unit length, something per unit area, something per unit volume For a linear density, something charge per unit length, we'll use the symbol lambda. For a surface density, say charge per unit area, we'll use the Greek letter sigma. And for a volume density, charge per unit volume, we'll use the common symbol Greek letter rho. Okay, so then what we can do is we can express, if I have my section of rod that is length delta x, what we can do is I can say, well, the amount of charge that I have in that length delta x is just that length times this charge density lambda. So in a section of rod of length delta x, we have a charge delta q is equal to lambda delta x. And so what I'm going to do is I'm going to put this lambda delta x in for the delta q in this expression, and we'll see where that gets us. Okay. So therefore, E net in the y direction was the sum. And so I'll put the sum of I, so this is over all delta q's. And then what did we have? We had Coulomb's constant times delta q. So we had Coulomb's constant, delta q, we're going to put lambda delta x. And then we had a z, and then we had a xi squared plus z squared to the 3/2. I think that's right. So let's compare these two. Yeah, all we did was change the delta q. That's right. Okay. Now, this is still not an easy sum to do, but what we're going to do is we're going to convert this to an integral. And so this thing is called a, you're doing math probably 101 or math 103 right now. And so this is the kind of thing that you'll talk about eventually if you haven't started already. So I'm not gonna, you don't have to worry about the details. You don't have to be able to do this calculation. But what I'm gonna say is that this expression can be evaluated as an integral, and you'll learn the techniques to do these kinds of problems so that the net electric field in the y direction would be given by the integral of ke lambda, and we'll put z here, and then we had x squared plus z squared to the 3/2, and then this is going to be an integral with respect to position x. And if our rod is very long, we have to integrate from x equals minus infinity to x equals plus infinity. And even this integral is not trivial to evaluate, but you will probably learn the methods to do it in your math course this term. I'm just going to give you the answer. The result is E net in the y direction is equal to 2 times Coulomb's constant times lambda divided by z. Using Coulomb's constant is 1/4 pi epsilon naught. We would get 2 lambda divided by 4 pi epsilon naught z. The 2 and the 4, we can do some cancellation. And so this would be E net in the y direction would be, let's see, lambda over 2 pi epsilon naught z. A fairly simple expression. And these are both valid expressions for the electric field a distance z away from a long, uniformly charged rod. So it's kind of interesting. There's an observation we could make. One is that when we had a point charge, the electric field was given by something like it was proportional to 1 over the square of the distance. Then, so that's a point is like 0 dimensions. And then we take a line of charge, and now the electric field is proportional to 1 over the distance. Okay, instead of 1 over the square of the distance. A line is 1-dimensional. What if we took a sheet? So we had a 2-dimensional sheet that was uniformly charged. What would you expect? How would the electric field vary with distance away from that sheet? Just as a guess. We had 1 over distance squared, then we have 1 over distance. What are we gonna get? So that's a reasonable guess. But it'll turn out that it will be independent of the distance. So it would be like 1 over the distance to the power 0. So in 0 dimensions for a point, it's 1 over distance squared. For a line, 1 dimension, it's 1 over distance. For a sheet in 2 dimensions, it would be independent of distance, 1 over the distance to the 0th power. Okay, good. So that's what I wanted to show you today. What I think I'm going to do in this last couple of minutes is just show you a couple of things about the lab. And so I'm going to go over here. And let me just show you how you're going to access the labs. There's no lab manual. Everything that you need to do the lab is available in Canvas. So I'm going to log into my Canvas shell here. All right. And so you're going to have different shells than I do, but one that you should have in here is Phys 121 Labs 2023. So if I click on that, I'm going to go into student view. And so what you should see should be something like this. When you go to a lab, you go to modules. And then the first lab that you'll do is lab 0. And so you'll have a module with all of the lab 0 materials. And so you can see in there that you're going to have like a syllabus, you're going to have a schedule, grade breakdown, safety documents. Those are all orientation documents that you're going to go over during this first lab 0. And then the manual is contained in these so-called Jupyter notebooks. And all you have to do is you just click on the link and it clicks on a second link and it'll open a new tab in your browser that will have this lab manual for you. You don't need to install any software. You can either do this using the lab computers or bring your own device. So if you want to do the work on your own laptop, all you need to do is connect to the UBC Wi-Fi and then have a working browser, and that's it. And then what it'll do is it will open for you your first lab manual. And so there it is. And so I'll talk a little bit more about this on Monday, but just to prepare for the labs, if you want to use your own computer, bring it to the lab with you. That's the only thing you need. If you don't have your own device or you don't want to use it, you can just use the lab computers that they have. So next week, just show up to your scheduled lab section. Okay, have a good weekend.